I'm going to do two families of subspace examples, which are so important that they deserve to get their own short video, which are examples that we've actually seen before, the null space and column space of a matrix. So we encountered these things when we studied matrices, but at that time we didn't know what subspaces were, so I couldn't really define them properly. So I'm now going to do this and check that those things really are subspaces. So I'll begin with the null space of a matrix. Let's let A be a M by N matrix with entries belonging to a field F. So maybe F is the real numbers, maybe it's the complex numbers, maybe it is the finite field of order 17, whatever, some field. Then the null space, which you write as N of A, is defined to be all the vectors x in F to the n, so that means all height n column vectors with entries from F, with the property that A times x is equal to the 0 vector. So that was our definition of null space. And now I'm going to show that N of A is in fact a subspace of the vector space F to the n. To prove that something is a subspace, we do it the same way every single time. We just check the three subspace properties. And the three subspace properties are, does it contain the 0 vector, first of all? Well, A times the 0 vector is equal to the 0 vector. So the 0 vector is in the null space. So I've realized I've not written down the name. This is the null space of A. Some people call it the kernel of A as well. You may hear that used. Okay, property 2 is closure under addition. So let's suppose we've got x and y, which are elements of the null space. And I want to show their sum is in the null space. So I need to work out A times x plus y. But of course, that's just ax plus ay, which is 0 plus 0, which is the 0 vector. So x plus y is in the null space. Okay, it's closed under addition. And finally, we can do closure under multiplication. So we'll let lambda be a scalar, an element of the field F, and we'll let x be in the null space. That wasn't a very good n. That's better. Then I need to show that lambda times x is still in the null space. So I just need to check what happens when I do A multiplied into lambda x. And one of the properties of matrix multiplication is that this is the same as lambda times ax, which is lambda times the 0 vector, since x is in the null space. And of course, when you multiply the 0 vector by a scalar, you get the 0 vector again. So lambda times x is in n of A. We have shown that the null space contains the 0 vector. It's closed under addition. It's closed under scalar multiplication, so it's a subspace. So that is one important subspace associated to a matrix. And we're next going to look at the column space and give an example of subspaces which is actually more general than it looks. So we're going to stick with our matrix A, but we're going to have some notation for its columns. So we'll let vector C1, vector C2, and so on up to, how many are there? There are n, be the columns of A. So these things are elements of F to the m. Those are elements of F to the m. So just look at an example of what we're doing here. For example, if A was equal to 1, 2, 3, 4, 5, 6, then the columns, well, this is 2 by 3 here, so n is equal to 3 and m is equal to 2, and the columns C1 would be the column 1, 4, and C2 would be the column 2, 5, and C3 would be the column 3, 6. Okay, so that's what I mean by the columns of A. I mean the column vectors which make up the columns of A. Okay, so what is the column space? Well, the column space C of A, by definition, is the set of all linear combinations of the columns of A. So it's defined to be all things of the form lambda 1 C1 plus lambda 2 C2 up to lambda n Cn, where lambda 1 up to lambda n are elements of the field F. Okay, that column space is a subspace of F to the M. And as usual, to prove it, we just check the three parts of the definition of being a subspace. So the subspace, the column space C of A is defined to be the set of all linear combinations. I want to show that the 0 vector is in there, but that's easy. I'm allowed to take any linear combination I like, and it's an element of the column space. So I'm just going to take the linear combination where all the coefficients, all the lambdas, are 0. So 0 C1 plus, and so on, up to 0 Cn is in C of A, by definition of the column space C of A. But that linear combination is, of course, equal to the 0 vector. Okay, so the 0 vector belongs to the column space. Let's do the next one, which is the next part of the definition, which is closure under addition. So I have to take any two elements in the column space. So let's call the first one. Well, I'm going to write this using summation notation just to make things a little bit easier for me. So the sum from I equals 1 to n of lambda I ci and sum from I equals 1 to n of mu I ci. That's what two arbitrary elements of the column space would look like. So I need to show that their sum is also in the column space. So I'm going to be lazy and miss off the limits because they don't really matter. What happens when I add this? Well, I'm free to group the C1s together. So I've got lambda 1 plus mu 1, lots of C1, and lambda 2 plus mu 2, lots of C2. So if I do this for all of them, I'll get the sum over I of lambda I plus mu I times ci. Okay, those lambda I plus mu i's are just some other scalars. So what you've got here is a linear combination of the columns again. So this thing is an element of C of A, the column space. All right, final part then. We take a scalar, lambda, and we'll take an element of the column space where the scalars are lambda 1 up to lambda n. Then if you do the scalar multiplication, so if you work out lambda times the sum of lambda I ci, then of course you can move scalar multiples through sums. So this is equal to the sum of lambda times lambda I times ci, which is a linear combination of C1 up to Cn. So it is again an element of the column space. We have proved that the column space is closed under scalar multiplication, so it is a subspace. Now, this is actually an example of a vector space concept called the span of some vectors, and so we'll return to it later on.